Okay, hello, logic class. Here we go. Bringing things kind of full circle a little bit. In previous classes and videos, I have brought to your attention this thing called the least upper bound axiom for the real numbers. I'll write it here. The least upper bound axiom for the real numbers says for any subset of the real numbers which is non-empty and bounded above. And that, well, let's just say any subset of R which is non-empty and bounded above has a least upper bound. Okay, and this is crazy because all new things are crazy, and assuming that you have never heard of this before until last week, then this is new, and anything that's new is weird and scary and crazy and hard. I am trying to tell you, and maybe you feel like a 19th century mathematician, that all along the real numbers that you've been using for your entire life have some kind of property. And not just some new property that I show you and you're like, oh yeah, ha ha ha, of course, I just never thought of that before. No, some fundamental property, some property which is so basic to the very existence of the real numbers that it in fact can't be proven and must be accepted as an axiom of the real numbers. And it is in fact like the distinguishing property of the real numbers. The magical property that when I add it to the list of the axioms for the rational numbers, suddenly we get, the real numbers. Okay, alright. Well, I forgive you for being scared. That's the gist of this, because it's kind of new and weird and everything. So, I suspect that perhaps you do not appreciate this axiom. Well, how do we appreciate an axiom? We see how it is used. You don't appreciate, say, the parallel postulate until you see, how Euclid uses it. You don't appreciate why we have some kind of postulate that says all right angles are equal until you try to do a proof and you sort of feel that, oh man, I really just need this statement. And okay, so it's in use that we come to appreciate the value or the wisdom of adopting a certain an axiom for a sort of well-known mathematical object. Okay, well, I got a theorem for you, and the benefit for you, my students, is that you already know this. You've already seen this theorem. In fact, you've even used this theorem, and in fact, this theorem is even in your basic calculus textbook. So you all took calculus 1 or 2 years ago in what I believe is chapter 9 of our calculus textbook. Is a long investigation of sequences and series. The calculus of sequences and series. The first section, 9.1, establishes what it means for a sequence to have a limit, and that is the epsilon n definition, which we did in pre-calc C, which establishes that a sequence has a limit if, no matter how close you need to be to that number L, I can go out far enough in the sequence such that the gap between L and the terms is smaller than epsilon. And then comes this theorem, which, okay, people call it different things, but I'm going to just call it what it is, which is the bounded monotonic sequence convergence theorem. It might very well be the name that our textbook gives it. What does it say? It says that if a certain sequence is monotonic, in other words, all the terms are increasing, do I even need increasing? I think sort of weakly monotonic, which is to say they're staying the same or increasing. So sort of non-decreasing, or alternatively non-increasing. So monotonic, either all getting bigger or all getting smaller. Then, assuming it doesn't grow without bound, then the sequence must have a limit. This is kind of incredible fact, which is not obvious at all. But the idea is, well, or maybe it is obvious. Okay, maybe first we just can draw a picture. So here's a picture. And the idea is that I have some sort of sequence. what's up with this sequence? Let's take the special case of monotonicity in which the sequence is increasing, or non-decreasing, as people say. All right, so I have, terms of this sequence, and the terms are getting, bigger and bigger over time. And another fact, not only are the terms getting bigger, but the entire sequence is bounded above, which is to say that there is an upper bound for this sequence. So there's some number, I don't know, let's call it like m, and I can say about this m that the terms of the sequence never go above m. Okay, so that rules out kind of infinitely increasing sequences. Okay, well, yeah, what then happens? Well, I have sort of like a term, and my next term is, either the same or a little bit bigger, and my next term is either the same or a little bit bigger, and, well, the terms are just getting bigger and bigger and bigger, but they don't pass m ever. And so, what this theorem says is that, in fact, they kind of settle at some particular value, and that value is the limit of the sequence. Quite amazing that I can infer that the sequence has a limit just from the fact that the terms are increasing and that they don't increase forever, or that they don't sort of keep increasing beyond any kind of bound. So that is that the sequence is bounded. All right, and I don't know how well you remember the sort of the details of the logical structure of all of the theorems from this time that you were taking analysis 1b, but actually this is absolutely essential, this theorem, this bounded monotonic sequence convergence theorem. It is the missing piece that tells you that certain sequences have limits, and in fact you use this theorem sort of over and over again. Now that I'm saying this, I should probably back this up. I think this is lies at the heart of many of the theorems that justify the proofs of the various tests for series being convergent and things like that. I'll maybe come up with some more examples in a minute, but we use this sort of theorem all the time. This is one of the basic kind of building blocks of analysis. How can we prove it? Well, I'll just tell you, I think all of you, I can say who's watching this, my own students, I sort of know who taught you calculus. It was either sort of Schwartz or Stein or maybe Kirk or something like that. And you did not prove this theorem. And even though the proof is actually right there in the textbook, so if you had tried or cared to, you could have read what the textbook had to say, and that would be that. And the reason why you didn't prove the theorem is very simple. The thing is that in order to prove this theorem, you need the least upper bound axiom. So this is exactly the kind of basic, you might say, theorem of calculus that they discover. I believe this is due to Weierstrass in the 19th century. But you prove it using the least upper bound axiom. So okay, let's go. Kind of rambling a little bit. I am going to prove that this sequence has a limit. How? Well, let's take. Well, maybe I just give it away right away, right? What can I say about the terms of the sequence? They're getting bigger and bigger and bigger and bigger and bigger and bigger. Well, just take all the terms of the sequence then, and the terms collectively are a set of real numbers. And this is exactly what the least upper bound axiom is designed for. It says that if you give me a bunch of real numbers, then there is a number which is just bigger than all those numbers. By the way, it could be one of those numbers. But there is a least upper bound. There is a sort of a number which is smaller than every number which is an upper bound for this sequence. So m here I've drawn is an upper bound, but of all the upper bounds, of course any number bigger than m is an upper bound, so there are sort of an infinite number of upper bounds, but among all the upper bounds there's a least upper bound. And then, big surprise, this number L is in fact the limit of the sequence. Whoa. Okay, let's go. Maybe we just kind of start the proof. So here we go. Let S be, just as I said, the set of all of the members of the sequence. So let this be, let S be, it's a little bit confusing because people use this notation for sequence, but so I'll just say let S be, the set of all the terms of the sequence. In other words, S is, I'll even just write it out, right? Let S be, S is the set of terms of the sequence. Okay, great. Well, S is bounded above. S is bounded above. That's built into the theorem into the hypothesis of the theorem that we're proving. S is bounded above, and of course, okay, by M, say, and of course, S is non-empty. S is non-empty because it's a non-empty sequence. Okay, so here we go. I have a set of real numbers which is non-empty and bounded above. So apply the least upper bound axiom. Apply the least upper bound axiom to this set S. And suddenly, come sort of falling out of the sky is a number, L, which is the least upper bound. Okay, so S has a least upper bound, call it L. The power of the least upper bound axiom is the ability to sort of conjure, almost out of thin air, this number L, which is a real number, this number L, and it is the least of all the upper bounds. Okay, great. Well, now I make a claim. Claim, maybe it's best to put it right here. Claim is that this is the limit. So claim the limit as n approaches infinity of this sequence is in fact L. Okay. Right. Well, this entire notion of a sequence having a limit is also built upon a certain kind of understanding, which is that this notion can be made precise, and it in fact has also been sort of arithmetized. So what must I show to show that this sequence has a limit L? Well, this goes back to something we did even in Precox C, that for any possible epsilon, no matter how small, and so here I will draw these two parallel lines as one does, and this is L minus epsilon, and this is L plus epsilon, and what I need to show is that for all epsilon greater than 0, there exists some number, big N, greater than 0, such that for all little n, if n is greater than big N, then the gap between, actually it's possible to just say it out in the chill way. The chill way to write it is without absolute values. So if n is greater than n, then the nth term of the sequence lies between L minus epsilon and L plus epsilon. Okay, so that's the definition of what it means for a sequence to have a limit. I'm going to prove to you right now that this sequence does have a limit, that this limit is in fact L, L being the least upper bound of the terms of the sequence, which I got from applying the least upper bound property. Alright, so now it's just you do it, right? So let's go. Okay, well, take some arbitrary epsilon greater than 0. Okay, so I receive my challenge. Now, I make a couple of observations. So since this sequence is monotonically increasing, I guess I want to just go across, increasing, then, and bounded above by L, and bounded above by L. In other words, I'm now using the property of L, not that it is the least upper bound, but that it is an upper bound. Then what is the relationship between L and the terms of the sequence? Well, the first term is less than or equal to the second term, which is less than or equal to the third term, etc. And all of these are less than or equal to L. This is what I know. Okay, well, so that means that L minus epsilon, since that is of course less than L, L minus epsilon is less than L. So since L is the least upper bound, and here I now use the definition of least upper bound, then we know that L minus epsilon is not an upper bound. Okay, this is kind of crucial, right? I have some monotonically increasing sequence. It's getting bigger and bigger and bigger. Then I know that L is greater than or equal to every single term in the sequence. Well, now, take the sort of lower parallel line, L minus epsilon. What can I say about it? Well, L minus epsilon can't be an upper bound because L is the least upper bound and L minus epsilon is less than it. So the very fact of being the least upper bound means that there can be no upper bound less than you. So if L minus epsilon is not an upper bound, then it means, as we see here in the picture, that there must be terms of the sequence which are larger than L minus epsilon. Okay. Thus, we must have terms of the sequence, say the nth term. Now I use big N to refer to a term of the sequence. That's what I said, terms of the sequence A sub n, which are greater than L minus epsilon. Okay, in other words, the conclusion of this kind of left panel here is that since L minus epsilon is not an upper bound, one may go out far enough in the sequence. What is the very definition of being not an upper bound? It means that L minus epsilon is not larger than every single term in the sequence. Therefore, there must be terms in the sequence which are larger than L minus epsilon. So let big N be the index of one of the terms of the sequence, not necessarily the first one, but of one of the terms of the sequence which is in fact larger than L minus epsilon. And I know there must be one because I know that L minus epsilon is not an upper bound. Okay, so what we conclude here is that that A sub big N is greater than L minus epsilon. But, of course, it's also true that all the terms of the sequence beyond big N will also be greater than L minus epsilon. And at this point, we are pretty much done. So I'm ready now to prove the thing that I need to prove, which is this statement right here, right? The main content of the proof that the limit of this sequence is L is the proof of this conditional. What happens? I get challenged with a certain epsilon and I respond with a certain big N. Okay, well if you're following along, then the proof is done now, right? Because the big N that works is simply the big N, which is the index of the first term of the sequence, which crosses over the line L minus epsilon. And because it's monotonically increasing, then I never fall back below that line. Okay, so just to actually execute the proof, here we go. Take Take any n greater than big N. So I'm proving the conditional now. What do I know? I know that L minus epsilon is less than A sub big N. But I also know that A sub big N is less than or equal to A sub n for any little n bigger than big N, because that's what little n is. Little n is an arbitrary index beyond big N. Well, I know that this is true because I know that the sequence is monotonically increasing. But I also know that A sub n is less than or equal to L because L is an upper bound. So if the arbitrary terms of the sequence have to be less than or equal to L, fact. The arbitrary terms of the sequence beyond big N have to be bigger than N, and N has to be bigger than L minus epsilon. So putting those all together, am I just done? Yeah. So L minus epsilon is less than A sub big N, which is less than or equal to A sub N, which is less than or equal to L. And so what have I really showed? I've showed that A sub N is between L minus epsilon and L. And of course, L is also, maybe it's simpler to do it this way in one big show-offy line, L is of course also less than L plus epsilon. And so actually I can get rid of these less than or equal to's because L minus epsilon is strictly less than A sub N, which is less than or equal to A sub N. So A sub N is bigger than L minus epsilon and is less than L plus epsilon. And I guess that's exactly what I was trying to prove. Okay, great. That's it. Goodbye.